Hey, thank you. Let me share my screen. Hmm, okay. Okay, so it's a recording and you guys are gonna put the video on the website.
Yes, so we have a
Okay.
website and a YouTube channel. We will put this on the YouTube channel and it will be synced on the website. Is that okay?
Uh, yeah, yeah, yeah. I think
Thank you
I
so
think
much.
it should be fine. We can discuss a little bit. Maybe some materials have not been yet published.
Sure, of course.
But we can discuss afterwards.
We can edit for you. Yeah, thank you so much.
Yeah. Um, and thank you so much. Thank you for the nice invitation by Professor Liu. So the topic is about the. I just check you guys the website. It cover almost everything about AI, and I'm talking about the very specific things, AI for neuroscience. So the title is a neural network approach for human visual learning. I prepared some slides. I don't know the professor is going to introduce me, so I prepare some slides to introduce myself. I'm currently a lead the PI at Shanghai Jiao University. So my primary appointment is School of Psychology. So my background is brain and cognitive science and psychology. And I have my second affiliation is Shanghai Mental Health Center, which is the largest psychiatric hospital in Asia. We accept over 1 million patients per year. So and I get my bachelor in Peking University, get my PhD in the University of Rochester in the United States in brain and cognitive science. So after that, I did my postdoc and in Minnesota and National Institute of the Health. And after that, I came back to China to start my own lab. So I'm very interested in the interdisciplinary research. So my background or my early days is about what all I'm care about is the neuroscience, the human brain, how human brain processes information. That's the topic of cognitive neuroscience. And but later on, I'm very interested in artificial intelligence. So if we combine together, for example, we try to use the AI knowledge or AI tool as a tools to study human brain, or more generally biological brain, from the monkey, primate brain or the mice brain. That's a traditionally we call it computational neuroscience. So it's not new actually. It was established in 1980s, I think. Um, um, okay, so the output of this type of research is basically trying to publish the papers in neuroscience journals. And also, if we go another way around, that we try to use the brain knowledge to create a better machine, better algorithm. That's the kind of we call brain smart computing. Actually, this is it's a very confusing term, brain smart computing, because uh, in my opinion, so my experience is that like a lot of different people with different backgrounds, they have a different definition of what is exactly brain smart computing. But but for me, that the ultimate goal is publish the paper in top AI conference or AI journals. And of course, as I said, I have affiliation, I'm appointment with the psychiatry. So I also do some research on computational psychiatry. So today of course I cannot talk about all of this stuff. So the topic of today is AI for neuroscience. So most of it is the how we can use the AI knowledge or as a tool to understand the model of the human brain for patient processing. So let's first talk about the AI. So I have to say, of course, we can see the very rapid progress of AI in the last 10 years. And as a neuroscientist or as a psychologist, we have to acknowledge that the progress of AI is much faster than the neuroscience. So this is true. And I think every neuroscientist have to agree with that. But the so when we talk about as we have think the AI as a very rapidly developed, then we at the I think the neuroscience or all other science, natural science, the research in all other natural science research field, like the chemistry or like the physics, material science, we all think about that, how we can use the rapid progress of AI, how we can utilize this type of knowledge to help our own research. That's AI for, I think that's my understanding of AI for science. So, but in my opinion, so if you look at the history of the AI, when we talk about AI for science right now, we talk about AI for physics, AI for chemistry, AI for blah blah, AI for biology, AI for protein. That's what DeepMind did. So, but if you look at all the different natural science, different fields, different disciplinary, which field has the closest relationship with had a tight relationship with AI? That's in neuroscience. That's brain cognitive science and psychology. So if you, for example, like give you a few examples, like these are all famous people in AI, in the field of AI. For example, Jeff Hinton, everybody knows that, right? So his undergrad is in psychology. His undergrad major in psychology. Maybe many people don't know that. The second is, for example, David Rumhout. David Rumhout is was a faculty member in Department of Psychology in Stanford until his death. He worked in the Department of Psychology. He's not a faculty member. His primary appointment is not Department of Computer Science in Stanford, and he developed the propagation algorithm. Of course, the third one is David Marr. David Marr actually to start his faculty position in Department of Psychology in MIT in 1977. And he, after 3 years, he was promoted to the full professor, and he died at the age of 35. We all know that, right? So, and right now, the most prestigious award, Mar Prize in computer vision, he and is named on the psychologist. And also the third one is the fourth one, James Michaelinan, so who is still alive. He is currently a faculty member of Stanford University. It's also in psychology. What I'm talking about, all these people, their primary appointment in psychology department, not in computer science. And we can focus on, for example, David Rumhout, and we all know that Rumhout and Jeff Hinton, like they published their foundation paper, like backpropagation. Otherwise, we have no way to train neural network back in 1986. Oh, sorry, 1986. And if you look at the Wikipedia, so the first definition of the Rumhout was an American psychologist who made many contributions, human cognition, AI, and blah, blah, blah. So his definition of the American psychologist, and not the AI computer scientist, American computer scientist. And also the International Society of Cognitive Science also offered David Rumhout Prize to the famous to like a very outstanding researcher in cognitive science. Of course, that you guys think this is over like 30 years ago, 40 years ago. That will go back in the 1980s. And after that, it seems very strange that like the cognitive science and AI they go in their different ways. They diverge. And so what I'm talking about is, for example, we all know the famous AlphaGo ChatGPT, right? That good example, the very successful example of AI. And for example, AlphaGo is developed by Demis Hassabis. Demis Hassabis is the CEO of DeepMind. I don't know whether you guys have know his background. If you go to Google and you go to Google Scholar and scroll down his paper and try to check his early papers, not right now, not the recent 5 years, very early paper during his PhD. And he published a lot of paper, for example, in psychological science and, for example, neuroimage and Journal of Neuroscience. All of these journals are very standard neuroscience and cognitive neuroscience journals. Actually, if you look at his PhD, he never published any single paper in what so-called top conference like SML and NeurIPS and or the like TPOMI and like AI journals. He never published this. And if I give uh uh this paper this CV and ask you, let someone guess who's this person? I might guess this person is a faculty or postdoc in the Department of Psychology in either in China or in the US. So it's very, very standard CV for the cognitive neuroscientist, not the AI. He's never, and after that he became an AI researcher and then founded the DeepMind. So I present some evidence that like if you go from the long go back, we check the history from 30 years ago, 40 years ago until right now, like DeepMind, for example, Hasabe's, we know that like the brain science and the psychology and the AI, machine learning, they have very close relationship. Somehow, uh, they go in different direction. Uh, that's because some context, like historical reasons. But I think that right now, currently, so it's a time for these two different directions. We can renew together. They can merge and to produce some good useful things. So let's talk about the AI for neural. In my understanding, of course, AI for neuroscience, different people have different definition, right? I'm just talking about my personal definition, my personal understanding. Uh, I think that is just a new name for compute as a computational neuroscience. Computational neuroscience very traditional is a traditional area, but specifically right now, everybody talk about AI for neuroscience. In my understanding, that like if you talk about computational neuroscience, we use, for example, classical machine learning, for example, symbolism approach, and to solve the neuroscience problem. But specifically, I know we know that like connectionism, especially like a neural network in the form of neural net, that's the most successful structure in the last 20 years. And what I'm understanding is that like I understand that we specifically uh, may need to use the deep learning framework, trying to that's a new thing, and that's the new tool trying to solve the neuroscience scientific question. That's my understanding of AI for neural. But there are two things. There are two key components. One is we have to use some. We need to use not have to. We need to use some uh, neural network, most sought models from the machine learning from AI. And second, you have to use this. The goal is to solve the neuroscientific question. That's not an engineer. Not that's not the like we increase the performance like three points into the accuracy that's from 90 to 95. That's not the point for AI for neuroscience. And I understand, but my understanding is really hard actually, because that's really need some interdisciplinary uh, background. Um, so so for this, I today I'm talk about like two studies, and just we finished it recently, and that's my understanding how we can use some neural net model to model how biological brain works. That's a goal. So firstly, talk about like perceptual learning in humans, macaques, and convolutional neural networks. Secondly, we're talking about like continual learning, how human can consolidate the learned knowledge in a continual learning fashion. So let's talk about the first thing. So if we talk about like perceptual learning is especially visual perceptual learning. That's basically exactly what is computer vision study. For example, like in human, like in our research, uh, I give a simple example. For example, I presented two couple, right? One's the 45 degree, and the second one is, for example, like 47 degree. That's only 2 degree apart difference. It's a very tiny difference. And we ask you whether the second one compared to the first one is clockwise rotated or counterclockwise rotated. That's a very simple laboratory experiment, human experiment, to test your orientation discrimination. And of course, it's hard, right? It's only very, very subtle difference. But the thing that like people found that if you ask the human subject and to practice, let's say I do this over 1,000 trials per day and practice like 7 days, and you will see that like the performance, human performance is going to improve at the learning. So that's how human visual systems learn a very specific task. And but the point is that is we all psychologists, we all design those type of tasks in a very simple and use a very simple task, use a very simple stimulus, and in a well-controlled laboratory setting. But if you look at the machine vision, the computer vision, that's a very different story. And for example, object recognition, video tracking, autonomous driving, that very standard computer vision task. Because computer vision, the goal of computer vision is just to learn some visual task in a real world, right? In a real world setting, and this tasks are very complex because only by this way computer vision is useful. Otherwise, that's useless. We want to make a product. So that's the big gap between the we are talking about the same thing, how human view system learn a task and how a machine view system learn a view task. Basically, we're talking about the same thing, but we use very different approach. And that's a gap, and how we can merge this, like bridge this gap. So if you look at the theory, why, or like human view system can learn those type of things, why training can make the performance better. There's some different theory about this. One type of theory, computational theory, is that like if you practice your view system and learn do this again and again, and the supervised training and increase the signal noise ratio of information processing in your brain. This has been proposed as a computational model, which is kind of true and reasonable. Because if you increase the signal loss ratio, of course you can get better performance in any machine, right? And also, if you, the neuroscientists also have run a lot of neuroscientific experiments. For example, if you look at the experiment, people look at the macaque. If you practice the orientation discrimination over days, and you can record the neuron in the V1 primary cortex, the tuning curve of the V1 get like sharpened. And also, for example, the final factor is reduced in the V1 neurons, or the correlation between two neurons also decrease. Also, at the population in the human brain, one brain area, like if you train such subject to do this after 10 days training, and the decoding, for example, the decoding accuracy increased. And also in the monkeys, for example, the total amount, if you record a bunch of neurons in V1 and after over training and to calculate how much information contained by this neural activity, and so drastically increased during the training. So that's how we have a lot of the experimental phenomena. But the question, so my question, the scientific question is, so we have the computational theory and we have a lot of fundings, empirical fundings, how we can link them together? That's a question. And I think, in my opinion, I think the neural network is a useful tool to solve this type of problem. So what we did is very simple example. AlexNet, very classical neural network. So AlexNet was trained on to do object recognition on ImageNet. So we use the the first 5 layers, pre-trained layers, and we take the 5 layers and output and connect to a decision unit, so the linear readout, a decision unit. And we treat this as a model of human real system. And we train this neural network to just to do this orientation discrimination task. For example, we input 2 images. One image, you get an activity. You input another active image and you get an activity. And you can make the decision that whether the second is compared to the first one is clockwise rotated or counterclockwise rotated. Of course, we increase the difficulty. For example, we add a different levels of noise to image to make it more and more difficult to this task. So basically, so how we bridge this gap, as I said, we use a neural network trained for complex tasks and treat them as a human visual system to train them to do some simple laboratory visual tests. That's our approach. And here the results in the behavioral y-axis is the accuracy, the higher is better. And you can see that the axis is just a contrast of the stimulus. So you have a drastic accuracy improvement in the pre and post training. And especially if we derive the threshold contrast threshold curve. So this one is measured by human. It's a human performance. Is measured into 1998, and this one is how we can derive from this neural network. As you can see, they're qualitative very similar. So this neural network, the performance, behavior performance is very similar to human, the learning performance before and after the training. And the next slide, I want to show how internal neural representation are very similar. So this is the what we found in the human brain, that the decoding accuracy after training the increase. And that's exactly what we found in the neural network. In the 5 different layers, in the first, the slightly decrease, but from the layer 3, 5, 3, 4, 5, they all just significantly increase the decoding accuracy. The second is that this is published in Nature Neuroscience in 2014, and in the monkey V1 over the training, the population information, visual information drastically increase. That's also we calculate that from the layer 3, such an increase become very significant. And this is, as I said, like the neuron V1, the monkey brain V1, like V1 neurons, the tuning curve is sharpened, become narrow after training, and that's exactly we found in layer 4. Actually, we found this effect from layer 1 to all layer 4. We only presented the effect in layer 4. And also, if you look at the real neuron, biological neuron, final factor and the noise correlation, they all decrease during the training. And we calculate the artificial neuron, the final factor of artificial neuron, and the noise correlation. They also decrease at the training. So my point is that like this neural network, very simple neural network, can reproduce a lot of, can explain a lot of empirical finding in neuroscience, in human brain or your monkey brain. So the DCM model orientation visual perception reproduce a broader range of psychophysics and human imaging and animal neurophysiology results. However, that doesn't answer the question. That only indicate our model is kind of a reliable model. That doesn't generate a new prediction how or related to our scientific question. So we can talk about this in the framework of a signal detection theory. I think a signal detection theory is kind of well established in both the psychology and in AI field. Like if you want to classify two things, right? And these two things generated two distribution in our brain. And if you want this two distribution become more discriminable, one approach is to make the two distribution further, right? And the mean of the distribution get further apart, or we can reduce the variance of the two distribution. And that corresponds to the signal enhancement mechanism or the noise reduction mechanism. But if you talk about, that's only one dimension. It's a one dimension distribution. If you talk about, for example, a population of neurons, for example, in the layer, there are many neurons in a layer in your network. So that's a very high dimensional distribution, and we create the neural manifold. So we can extend the signal detection theory in a high dimensional response space. For example, if you want to discriminate like 45-degree or 47-degree, two very similar orientations, we can present the one stimulus many times. That creates a distribution in a high dimensional distribution. And the two stimuli to be discriminated corresponding to two high dimensional distribution. And we can simply draw a linear classifier, for example, SVM, right? We can draw a hyperplane and to classify them into two different categories. That's how we do this, right? So so then we can use this type of idea. We know that perceptual learning can make the decoding better and make this two stimulus representation two stimulus more discriminable. And what's the possibility? One way you can do like the two distribution get further apart. That is going to predict the distance, the Euclidean distance between the mean of the two distribution get larger. but we tested this. Actually, it's not. Right. So signal hospital, and then another mechanism, for example, the whole manifold somehow shrinkage. If you reduce the variance of the two high difference distribution and make this two distribution get more discriminable, that's exactly what we found in the DCN model. And we tested this with different layers. After training, after learning, practice this, the artificial neuron variance drastically decrease. So it's a manifold shrinkage rather than signal enhancement is a primary mechanism of orientation VPL in DCN model. Of course, we can further look at this. In a high dimension, we can do this way. For example, the shape of these two manifolds, somehow the position somehow just rotated, right? Somehow the covariance, the ellipse, the direction of elliptic covariance is the same as the direction of the two mean. Then we can rotate this two manifold and make it orthogonal. And of course, that will reduce the overlap between two, make the two distribution more discriminable. That we call the signal rotation. And we look at the five layers after training. In the layers, the high dimensional representation space is rotated around like 60 to 70 degree. And also we do some, we call the fourth one, a manifold warping. For example, the position of the mean that did not change at all, but somehow the direction of the covariance somewhere rotated. Also that's gonna reduce the overlap between the two distribution. And we tested this. That also the case. You can rotate this. But the question is, so our finding is that like those type of visual perception learning systematically warps the representational geometry in the DCN model. It's a high dimensional neural space. How we can quantify this type of different things? We consider this a four mechanism, and we consider the gradient, like salt, pepper, and I don't know, like you can add them one by one and test their effect. And that gives you the very unique pattern of this. So not all the gradient make a positive contribution. As you can see a very large, in all five layers, there's a very unique increase first and a decrease. It's a unique pattern so about how different gradients contribute to the whole population active information. So so after we further investigate the DCN model, we have three predictions. First is that so the overall variance of the manifold shrinkage rather than signal enhancement is a primary mechanism of real perception learning. And also real perception induces two novel mechanisms we call signal rotation or manifold warping. And also if we do some information theoretical analysis, they reveal very unique pattern from different gradients. But what we talk about right now, we'll talk about the neural network. Neural network is just a model. It's just a machine. They're not biological brain. So the next thing what we do is, can we test these predictions in real brain, in the human brain or in the monkey brain? The first thing we do is we train another neural network to do the motion direction discrimination. So to test whether this type of result actually is very unique to that specific model or is more generalizable to other models structure. And this is a behavior accuracy pre and post. The accuracy this model behaviorally, the performance increase a lot after training. And we also found that after training from late layers, get a significant increase in the population information. And we can focus on, for example, layer 6 as you can see the largest improvements of the training. We can, for example, we analyze how these two distribution in the high dimensional space, whether they increase the distance, actually to know. And we can check about the response variance, and you could reduce a lot. Just you can see a very significant reduction in response variance. And also whether we can see such rotation, and very surprisingly, they rotated around like a 50 degree, very similar to the previous model. And we also see manifold warping. And we also see very unique pattern, like we analyze the layer 6. if it increase and decrease. So that's another model. Very completely different model, different architecture, different task. We verify this prediction. And also, we trying to do some human experiments. And we collaborate with Fang Fang and Professor Fang Fang, Professor Li Shen in Peking University, and Professor Jia Ke in Zhejiang University. We asked 22 human subjects, training them 10 days. And pre and post, we measure the neural activity in 60 different brain regions in V1, V2, V3, and V3A, human MTI, IPS. That different just human visual cortex and in the occipital cortex. And we can see that in two motion selected region, V3A and or the HMT plus. So these two regions basically is responsible for processing motion information in your brain. And which makes sense because of the stimulus, the task here we just to discriminate two motion direction. And we take out this, we further analyze the activity in these two brain regions. And the prediction is that, again, the two distribution in the representation of two distribution in the high dimensional space is there's no significant improvement, but the response variance has a very significant reduction. And also we see a very consistent around a 50-degree rotation in this two brain region in the human brain. And we also see the manifold warping. So remember that like previously we talked about artificial neuron in neural network. Currently we're talking about MR response. That's the voxel bold response in human cortex. And also we analyze the pattern. We can see a very consistent increase and a decrease pattern. But here's a human brain. We further tested this in the monkey brain because in the monkey brain, we can actually to record the activity of the biological neuron. And that we collaborate with Professor Chen Xin, Professor Alex Seal. They are in University of Manchester, the Newcastle in England, right? And we recorded two monkeys. They are doing the contrast discrimination task, and we reported many neurons in monkey before here, and we can track how these neurons activity of this neuron change over the course of the training. They train the monkey like I think many days. And here's the behavior experiment, behavior accuracy. There's 6 conditions. The monkey improved a lot, which makes sense, which means that the monkey actually it learns to do those things. And we see the very drastically increase in decoding accuracy or feature information. Again, we test our prediction that whether these two distributions get further apart, no. Now, whether these two distributions shrink, it's going to become smaller, yes, because the overall variance drastically decreased. And also that's a 50-degree rotation, and we see a manifold warping. And also we see a trend like if you go up and going down, although this is not that significant as we previously described. So to make the summary is that like we start this by neural network. And the beauty of the neural network is that we can measure and we can understand the activity, all the activity, all the neurons. We can visualize all the neurons. We can visualize the connection of all the neurons. But even the very sophisticated like approach record method, actually we cannot do this in the monkey brain. It's very hard. So that's why the neural network becomes useful. So we generate prediction, we test in humans and we test in macaques. We found a very consistent learning mechanism when the view system learn, no matter the artificial view system or biological view system, learn to practice a neural task and getting better and better. The mechanism is exactly the same. So the population activity analysis reviews shared mechanism with VPR in human, macaque, and decent. So this is already we published the preprint and it's under review. If you have an interest, just